Alrighty then. Morning, happy Wednesday. Today, just want to quickly remind you that your lab for Monday is due tomorrow. And dealing with the identifying the chemical bonds. Today we're going to move on from Lewis dot structures, which are just two-dimensional representations of the bonds between atoms around the central atom and the electron configuration. Today we're going to start talking about the three-dimensional shapes or the molecular geometry of these. What do they really look like in 3 dimensions? We want to be able to explain them in terms of the Vesper theory. We'll talk about what the Vesper theory is on the very next slide. We want to be able to draw these three-dimensional models. And then tomorrow in our small group, we'll introduce being able to identify sigma and pi bonds and being able to draw the polarity for these three-dimensional models. So the first thing you're probably wondering is, why is VSEPR pronounced Vesper? As you try to pronounce it the way it is spelled. So Vesper isn't quite as easy, or just doesn't roll off the tongue the same. But this is what it stands for. So on the bottom left-hand portion of your note-taking sheet where it says VSEPR, I would strongly encourage you to write valence, shell, electron, pair, repulsion. And this is the repulsion between these pairs of electrons in the valence shells is what drives the shape of these molecules. Another thing I would encourage you to do, if you have it available before we get started, is to take out your iPad, because I'm going to be showing you some stuff on a PET website, PHET. I believe Mr. Gussie sent you that link about an hour ago. If you have your iPad with you and you want to log on to that website, you can manipulate these little models yourself, so you can kind of see what happens if and when as you make changes as I'm going through it with you. So we're going to start simply and get more complex. You got a couple of bold letters on that note-taking sheet. We've already identified what Vesper stands for. The steric number, which is the heading across the top, refers to the number of electron clouds that we're dealing with. And more specifically, it's the number of electron clouds around the central atom. Hopefully you recall when we did our Lewis dot structures, there were a number of things that we were asking you to focus on. Valence electrons and total electrons, but we were also asking you to identify or focus on identifying that central atom and the symmetry when you're drawing your two-dimensional representations. So the number of electron clouds around a central atom. Electron clouds can show up in a number of different ways. Not too many different ways. It's pretty simple. The first way is just a single bond. If you've got a single bond between a central atom and another atom, those two shared electrons are going to represent an electron cloud. But in the same way, if it's a double or triple bond, instead of having 2 shared electrons producing this cloud between the 2 atoms, you're going to have 4 electrons zipping around in this same cloud of space for a double bond, or 6 electrons if it's a triple bond. But even if it's, whether it's 2, 4, or 6 electrons, they're all in the same space, they're all in the same cloud, it's only going to be considered one cloud. And the other way we can get an electron cloud is just from a lone pair. That would be a lone pair, again, that's around the central atom. We don't care about lone pairs on the outskirts of our molecule. So you don't have to draw this. I'm just going to sketch a couple of very simple examples to illustrate how we can identify electron clouds. NH3 is a Lewis dot structure that we just drew last week on our test. And every time I use this thing, it has to be reset. So if we have NH3, our Lewis dot structure would look like that, where we got 3 hydrogens around our nitrogen as our central atom, and we would still have 2 unpaired electrons. That's going to be our lone pair. That gives us 1 cloud, 2 clouds, 3 clouds, and 4 electron clouds. Another fairly basic example would be SiO2. When you did that the other day, hopefully you got 2 double bonds, 1 double bond between each oxygen and the silicon. So this represents 1 cloud, that represents another cloud, so for this one we've got 2 electron clouds. 2 electron clouds would give us a steric number of 2. 4 electron clouds would tell us our steric number is 4. And as I just mentioned, we do have unpaired electrons on the oxygen out here, but that's not our central atom, and so we're not going to count those as electron clouds. So our first and simplest shape, when you see the letters off to the left, PG, that PG stands for parent geometry. And our simplest one is steric number 2, where we've got 2 electron clouds. So this is the PET simulation, that the link that Mr. Gussie sent you. In this example, the purple atom is our central atom. We've got 2 bonds. These are 2 single bonds. If we replace that with double bonds, you'll see that the shape doesn't change. It's still a straight line formed between the outermost atom on the left, the central atom, and the outermost atom on the right. Why do you think that would form a straight line or a straight molecule? Why would the electron cloud on the left be completely opposite of the electron cloud on the right, as opposed to being, say, here or here? What are the electron clouds made of? Electrons, which have what kind of a charge? Both of them are going to be negative, and we know, hopefully, that since they're the same charges, like charges are going to repel. So if these 2 guys were sitting here and here, they're going to repel and they're going to push away from each other as far as they can. If they go any farther than this, now they're getting closer together again. That's no good. So they're going to stay as far away as they can, which is why they're going to form that 180-degree angle between the two bonds and form what we would term as a linear molecule. And you'll be able to see that even if I try to somehow squish these together, they won't stay together. So we're going to have 180 degrees in our first shape. Parent geometry is linear. This is going to be such a simple little diagram. We are always going to represent X as our central molecule, or our central atom, sorry. The line represents our bonding pairs of electron. So here we've got two BPs, or two bonding pairs. And at the end of each of them, we have our other atom. So two electron clouds, this guy and that guy. Which gives us the steric number of 2. And 180 degrees between the bonding pairs. So we're going to, for each of these set of diagrams that we sketch and label, we're going to be identifying the bond angles. Angles are always measured between bonds, not between bonds and lone pairs. Which, if you look just beneath your linear diagram that we just made, you see one LP. LP refers to lone pairs. If we took one of these bonds out and replaced it with a lone pair of electrons, that's not going to be a very difficult shape to draw. So we just have two atoms together. At the top of the sheet, or just under the steric number, you'll see hybrid. What's happening in these molecular geometries are we're combining orbitals. We learned earlier about the s orbitals, the 3p orbitals, and the 5d orbitals. So in our simplest shape, steric number 2, we have an s orbital and a p orbital. They're kind of overlapping. They're combining or hybridizing. And so we refer to this hybrid for steric number 2 as simply SP, or SP1. And as we just said, in this case the bond angle is 180 degrees. And that's obviously going to be the same whether measured from left to right or right to left. That's easy, right? Okay. What's going to happen if we add another bonding pair? Throw that guy in there. You can see that immediately what was a 180 degree angle squishes, because these two guys want to get away from that guy. And it doesn't matter whether these are single bonds or double bonds. If I take this guy out and replace it with double bonds, we still get that same orientation, the same shape. This electron cloud is repelling these electron clouds, but this electron cloud is repelling this electron cloud, and they all want to get as far away from each other as they possibly can. And so the orientation that we're going to get for that is simply 3 bonding pairs that are all in the same plane. They're all in the same plane. And they're as far away from one another as they can get. Because if we put one up here, that's a lot closer to either of these than it was before. So this is the orientation that's going to get each of these as far away from the other ones as possible. So they're all in the same plane. It's 360 degrees around. We got 3 bonding pairs. Now we got a lone pair. That's fine. So each of these angles is going to be 360 divided by 3, or 120 degrees. So this one also is going to be the easy one to draw. Our previous hybrid was one s orbital combined with one p orbital. When we had another bonding pair, we introduce another p orbital. So now our hybrid is going to be sp2. As we just said, our bond angles are going to be 180 degrees, 120 degrees, so to the best of your ability, you're going to draw 3 lines that are equally spaced. 120, 120, and 120. So we got 3 bonding pairs here. And the name of this, again, is trigonal planar. It's a triangle formed by our outermost atoms, and they're all in the same plane. They're going to lie flat to stay as far away from one another as they can. If we remove one of those, we're back to steric number 2, but if we add a lone pair in place of that, now these two pretty much have the same orientation as they did before, because just like before, we got electrons here, we've got electrons here, and the lone pair is still electrons, and so they're going to repel the electron clouds from our double bonds or single bonds, whichever the case might be. And so it's going to be pretty much equally spaced all the way around that central atom like it was before. The very minor difference is that our lone pairs repel just a little bit more than our electron clouds do, or than our bonding pairs do. And so our angle, instead of being 120, is going to be just slightly less than 120 degrees, because when we have a lone pair here, it's going to push these guys a little bit further away, which is going to force them a little bit closer together. Still going to have the same hybrid. Within a given steric number, the hybrid is always going to be the same. So steric number 3 is going to be sp2, regardless of whether it's trigonal planar or whether it's bent. Sketch, not very difficult for this guy. I typically put my lone pair on the top, but you don't have to. And you're going to have your other two, this angle is just going to be a little bit less than 120 degrees. As I mentioned before, I think I mentioned it before, we only measure the angles between the bonding pairs, not between the bonds and the lone pairs. And when we describe the shape, we don't see the lone pairs. We're just describing the shape of the molecule between the bonding pairs. So those first two are easy. They do get progressively a little more complex, but I don't think it's terrible. Get rid of that lone pair. That takes us back to our trigonal planar. And if we throw in another guy, now we go from being planar to, whoops, kind of like a tripod. And you can see that when that guy comes in, it pushes the other three down a little bit. Pushes them away. He's out, he's in. He's out, he's in. And they're going to arrange themselves again so that they can be as far away from one another as possible. Our geometry for this is tetrahedral. Tetra meaning 4. And these guys are going to rearrange themselves a little bit. Not that sticky. So it doesn't matter which, especially if I did a nice job with this model, which I probably didn't, but it doesn't matter which side we place this on. This guy should be pointing straight up, and we got a tripod around the bottom. Straight up, tripod on the bottom, straight up, tripod on the bottom, straight up. You might recognize that immediately as being straight up, tripod on the bottom. So, the first one is our tetrahedral. That's when we've got 4 bonding pairs. This is the first one that we're going to have to draw that's going to be 3-dimensional, because as you can see here, one of these 3 tripod legs is coming towards you, one of them is going away from you. Before, everything was in the same plane, so we could just draw it on a flat sheet of paper. But if we orient it like this, our vertical one and the one that goes off to your right are in the same plane, but then you're going to have one that comes towards you and the one that goes away from you, and that's where things get just a little bit dicey in terms of drawing them, but with a little practice, it's not so bad. So X is our central atom. Do that every time and it's not right. X is our central atom. Y goes up vertically. The other one that's in the same plane goes down a little bit. Really doesn't matter whether you draw this one that's in the same plane to the left or the right. But ultimately you're going to have to show one that comes out of the page. And we do that by drawing a wedge. It starts small and gets bigger. And just for emphasis, make that Y a little bit bigger because it's closer to you. And then there's another one that's going back into the page. And that starts as like a dash that gets smaller and smaller. And we make that a small y rather than a big Y. Wouldn't expect you to know those angles. I figure you can take 360 and divide it by 3, but when we have our tetrahedral, each of these angles is going to be 109 and a half degrees between any two bonding pairs. So we still only have one bonding angle. There's 4 of them that are 109.5 degrees each. So what's going to happen if we replace one of those bonding pairs with a lone pair? Take one of those guys out, put the lone pair in, pretty much the same shape. The only difference is that, again, the lone pair of electrons are a little bit stronger in their repulsive force than the bonding pairs, and so this angle ends up being about 2 degrees less for each lone pair that we add. So instead of 109.5, now it's going to be about 107 degrees. We don't draw the lone pairs as part of our shape, and so that's going to look basically just like a little tripod or a 3-sided pyramid. We take this guy off, we got a pyramid with a face, and another face. So that's why it's called Trigonal Pyrimidal. Trigonal Pyrimidal because it's a 3-sided pyramid. So for this guy, we got 3 bonding pairs, 1 lone pair. Hybrid is going to be the same. It's still sp3. Hybrid remains the same within a given steric number. And the bond angles, as I said, are going to be just a little bit less because of the extra repulsion of that lone pair. Typically put the lone pair on top, but you don't have to. And the bottom is going to look just like it did before. Where those angles have shrunk just a little bit from 109 down to about 107. And we only have 3 more that we're going to do today, and then we'll stop, hand out your homework, and go through a couple of examples with you. Any questions on this guy? Struggling today. Wanna go get a drink or something? Alright, if we take out another one of our bonds and replace it with another lone pair, we still have a 4-sided figure, but again, we're only drawing the bonding pairs. So now, hopefully you can see that clearly, instead of being a linear, looks like a bent molecule, and that's where the name bent comes from. So for this one, we're going to have 2 bonding pairs, 2 lone pair. Hybrid remains the same. Bond angles, because of the extra repulsion of those lone pair, decreases by another 2 degrees. So we went from 109 to 107, 107 to 105. So really you only need to remember the 109, because if you can remember that 2 electrons gives you 2 degrees. got our lone pair on top. And it's totally up to you where you put your other lone pair. Mr. Gussie, Mr. Kelleher, is there any advantage or disadvantage to putting the second lone pair anywhere in particular?
No.
See, that's what I said. That you recognize immediately as a 5 for 105 degrees. What happens if we add another lone pair in place of one of those bonding pairs? We end up with just 2 atoms sticking together. So this is what we get when we have 2 lone pairs. This is what we get when we have 3 lone pairs. I don't think we need to draw that one. All right. This is going to be our last steric number that we go through today, and we're going to get through 2 of these, I think. Here's our Trigonal Pyrimidal. Throw this guy in, get rid of this guy and this guy. There's our tetrahedral, and when we throw in another one, they rearrange themselves to get as far away from one another as they can. And you'll see that the 3 legs of the tripod get pushed back up, and it would make sense because they're getting pushed equally from the left and the right, or from the top and the bottom. It wouldn't make sense for them to be closer to this bonding pair of electrons than it is to that one, or vice versa. So this guy's pushing down, this guy's pushing up, and they're going to end up back in the same horizontal plane. So here are the verticals. And then in the horizontal plane, we're back to our planar triangle. These guys are all going to be in the same plane. These guys are going to be in the same plane. That's as far away as they can get. But now, we got a bunch of angles to identify. How many different angles do we have between the bonds? Well, on the horizontal plane, just like before, we've got 120, 120, 120. In addition to that, what other angles do we have? Cool. A 180 between our top and bottom. And we're also going to have 90 between our top and any of our horizontal ones, or our bottom and any of our horizontal. So we're going to have 90, 120, and 180. Whole bunch of bond angles to identify. So we've got 5 bonding pairs. We went from SP to SP2 to SP3. So the hybrid for this one must be
SP4.
That's a good guess, but we only have 3 p orbitals. So once we run out of p orbitals, we're going to start hybridizing with our Ds. So it's going to be SP3, whoops, I don't have it in there. SP3 D. 5 bonding pairs, 1, 2, 3, 4, 5 orbitals. And I'm sure we're getting good at these diagrams now. So in the vertical plane, those guys can all be in the same plane. So we got this guy and this guy that are in the same plane. If we rotate this a little bit, then the one coming to your right can also be in the same plane. And then we only have to worry about drawing 2 in either coming in or out of the paper. So this time, that guy is going to go horizontal because these 3 are all going to be in this plane rather than switched down like they were before. So these 3 are all at the same level. And you are hopefully better at drawing that than I am, but that's what those are going to look like in our bond angles. Bless you. 90, 120, and 180. So we get 90. And 180. And between any of those 3 in the horizontal plane, we're going to have 120. I think if I try to label those at diagrams, it's going to get really messy. Alrighty, last one that we're going to deal with today. If we replace one of these bonding pairs with a lone pair, we're going to get a diagram or a molecule that looks like this. And you'll see that it's labeled on your sheet as Seesaw, and this is why. So we still have our 2 vertical legs. This is like the plank of your seesaw, and the 2 legs that are in that horizontal plane represent like your fulcrum, and that guy just goes back and forth like that. There's your seesaw. That's pretty neat. So for that guy, we're going to have 4 bonding pairs, 1 lone pair. sp3d, same hybrid within a given steric number. I actually didn't mean to draw that line, but it doesn't let me erase it. So, and again, it doesn't matter where your lone pair goes, as long as it is one of the 120 degree bond angles that it replaces. So it's not going to be either of your vertical lines. We still have 120 there. We still have 90 there. And we still have 180 from top to bottom. So I hand this out, go through a couple of examples with you. And we have about 12 minutes left, so probably two or three examples and we'll be done. Yep. First one I'd like to do with you is number 10. We referred to that one earlier at the beginning of the presentation when we talked about identifying electron clouds. If we went through our TV process, we would find out that we have three hydrogens, each with single bonds around the nitrogen, and one lone pair. So this is what you should draw in that first vertical column where it says molecule and Lewis structure. So we're telling you what the molecule is. You're going to sketch that Lewis structure. You don't have to do this, but I'm going to do it at least once here just to reinforce that these are the 4 electron clouds. So in that second column, when it says steric number, or electron clouds around the center atom, our steric number is going to be 4. Parent geometry for steric number 4 is always going to be tetrahedral. If there are no lone pairs, if all the electron clouds are a result of bonding pairs, then your parent geometry and your shape are going to be the same. But as we just determined, as we just showed you as we went through some of these diagrams, as you go down the column with the parent geometry, as we had lone pairs, the shape changes a little bit. So in this case, we've got one lone pair, 3 bonding pairs. We've got normally our tetrahedral, but now we've removed one of our legs of that tetrahedral, and we got basically a tripod. Tripod is a 3-faced pyramid. So 3 bonding pairs and 1 lone pair gives us Trigonal Pyrimidal. So that is your shape or your molecular geometry. And then in the 3D structural formula, that's what we're going to draw. And the difference between what we drew before on your note-taking sheet and this is simply that instead of X's and Y's, we're using the actual chemical symbols from our elements. Normally our tetrahedrals are 109 because of the lone pair. It would be 109 minus 2 or 107. And the hybrid, steric number of 4 means we're going to have 4 orbitals combining. S, P, P, P. sp3 gives us 4. That's not so bad. It's not so bad. Let's do one to mix it up just a little bit. Let's go back to number 4. C2H6. Lewis dot structure for that. Looks like that. Now we do not have 1, 2, 3, 4, 5, 6, 7 electron clouds around our central atom because we really have 2 central atoms here. We got a carbon with 3 hydrogens and another carbon bonded around it, or the other carbon that's got 3 hydrogens and a carbon bonded around it. So if we treat this as our central atom, we've got 1, 2, 3, 4 electron clouds. 4, 1, 2, 3, 4 electron clouds. So our steric number is going to be 4. Our parent geometry tetrahedral again. Next column is our structural formula. So this guy is going to be a tetrahedral, and this guy is going to be a tetrahedral. So really we've got 2 tetrahedrals that are connected. So let's just draw one first. Got our carbon. Hydrogen. Hydrogen. And carbon. And then off of this guy, hydrogen, 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 hydrogen. May not be the best drawing, but...
You got too many questions up there.
Oh, yeah, I do. Thank you. Let's see. If this guy's in the same plane, this guy should, well, this one of these has got to come out. All right, so if this guy's in the same plane, then we're going to have to send this guy back a little bit. That's a good catch. Because we have no lone pairs, Our molecular geometry is also going to be tetrahedral still. Angles. .5, you recognize that immediately as 109.5. It's 107 if we have a lone pair that pushes our bonding pairs away a little bit. If there is no lone pairs, then it's going to be 109.5.
Oh, yeah. What's this, SP3?
And because it's steric number 4, it's SP3.
Yes. Yes. No problem.
Giddy up. Not to worry. You got a lot of information today. A lot of big multi-syllable names and drawings to draw. But you get plenty of practice. We'll do a lab that's got actual molecules that you can build out of little pieces of plastic.